On my midterm and on my final exam, I always have an inverse kinematics problem for a robot. I like these problems because they require visualizing the reachable workspace of the robot, quantifying that workspace, and setting up a solvable trig problem. With that said, these are the hardest problems on my test. They're worth about 25% of the test, so I want to show you how you work one of these problems. Before I go too far, I want to remind you that these worksheets are available in PDF form, both the solutions and the problem, on the link in the description. Go ahead and pause this video, go print those off, and you can see if you can solve them and then compare them to how I solved them. So the first thing you do is you look at the robot and get a sense of how it moves. So I always give a 3-link robot. This robot has 3 degrees of freedom. It's got a θ1 where it rotates around this base. It's got a d2, the amount that this joint here can extend, and it's got a θ3, and that's how much this joint can rotate around this base. And so these all have to follow the Navitt-Hardenberg conventions. So before you get started, it's important to know what is the range of motion for each of these. So we'll start with θ1. So θ1 defines which direction the x1 extends with relationship to x0, the base frame. So this coordinate frame here, in its nominal position, this arm would be pointing along this x0, and then it can rotate, and it can rotate all the way out for pi radians. So we're going to be able to sweep out an arc. Anytime you sweep out an arc, the rest of that robot, every point on it, is also sweeping out an arc. That is pi radians. And so now let's move on to this next joint. This prismatic joint is moving along the z1 axis, and it can move from 1 to 2. So its shortest position, it's a length 1. Its longest position is 2. This arm, for the previous joint, the radius value is 2. So this could be 2 or it could be 1 extending out here. Then we have a step upwards along our z0 axis of length 1. And then we have our final degree of freedom. And this one can rotate, and it says when θ3 is 0, it would be pointing straight up. And so it can rotate, we'll use the right-hand rule here. It can rotate a positive pi over 2, so it can stick all the way out to the side. And it can also go negative pi over 2, so it could rotate towards the center. And this arm is of length 1. Now, how I set up these problems in the exam is I always ask people to draw and shade a cross-section of the manipulator's workspace, and I'll give 2 to 3 of these little boxes where people can draw that out. And I'm looking for very specific things to see if they're visualizing this workspace correctly. And one of the big things is that they need to label all radii. They need to shade in that workspace. If not a one-dimensional set, if it's an open area, they've got to shade that in. And then I want them to label all those radii to make sure that they understand those trig problems. Now the next step after they do that is then they have to solve the inverse kinematic problems. Sometimes I give them a hint by the order of these problems. Here I'm asking for θ3 first. d2, the star here, just means that is the variable in the DH convention. So d2 asterisk. And then θ1 I'm asking for last. Often that's a little bit of a hint to tell you that one of these is easier to solve than the others. With that, let's get started. After I show you how I work this out, and then I'm going to show you a reminder of why inverse kinematics matter. Then I'll show you a simulation of this, and then I'll end with showing some computer-generated drawings. A little better than what I do with my pencil. However, I'm doing this with pencil because that's what they get on the exam, and so it's important to practice how you'll perform. But we're going to get started with this first one. And we're asking for the x1, y1 cross-section of the manipulator's workspace at a certain z1 equals 1. So before you even start drawing it, figure out on this robot where this frame is going to be. So I've identified here is y1 and x1, and notice they are pointing, y1 is pointing downwards, the opposite direction of where x2 is. Now I look on here and I've got x1 pointing to the right. I've got y1 that is pointing upwards. So that's actually opposite of what this is. This first joint is going to be lower in this axis. And then we're going to be measuring this at z1 equals 1. So here is z1, and I can move that out here 1 unit. And I notice that that's just at the lower limit of my d2 of my extension of my second joint. All these are going to be key in order to draw that. So, I'm only at one extent. Is this actually a robot going to touch this plane? Everything else is going to be out of plane, Z1 values that are farther out of this plane. So what I always do is I like to draw these robots. And so I know where 0, 0 is, and so I can draw in the background here. This is my prismatic joint. X1 is pointing out this way, and so in the opposite direction is where the rest of the robot is. It's actually 2 units over here, and somewhere over here was that first joint. Now that is necessary, but now I need to march forward from this. And I notice that my arm is pointing in the opposite direction of Y1. And so I can draw this arm coming downwards to 1 unit, and that is where my rotational joint is. In the nominal position, that's pointing straight out, so that's coming right down here. So the tip of my robot is right here at my nominal position. And then it can rotate into a plus and minus pi over 2. If it goes in a minus pi over 2, it's going to be coming out this way, which would be towards my arm. It would be in negative 1. So the minus is going to be out this direction. This is minus theta 3, and this is plus theta 3. They can go pi over 2, and so that's the radius of a circle here. So that radius is going to come over here, and then if it goes negative, it can go over here. So now I've drawn my workspace. There's nothing to shade because it's a one-dimensional set, but I do have to label the radii. So I'm going to just say that this is r equals 1. So this one is relatively easy. You'll notice that's why it's only got 2 points. This one over here is worth 8 points, so it's probably going to be more challenging. But the process is the same. I am drawing this in the x0, y0 plane. So x0 is here, this green arrow here, that's y0, and z0 is pointing out. That's the axis I rotate around. And so what I like to do is to draw my robot at the extents of different parameters. So let's start here, and we're going to draw this robot looking down from the top. And I've got a couple other pictures here, because sometimes it's hard to visualize the robot from just a single view. Here's a top-down view. Here's another orthographic projection, just to see how these different joints move. Let's draw this robot. This is my Z0 axis. It can go over to the right 2. This is a solid arm that's coming over here. And then we've got our manipulator. Our prismatic joint is pointing upwards. And that can go from 1 all the way up to 2 as it prismatics in and out. And then I am looking at the manipulator's workspace at Z0 equals 2. So I've moved 1 unit up here, and then I move another unit up here. So I'm looking at the plane that just intersects this. The only way it can get it is when it's when this manipulator is laying flat. When theta 3 is either pi over 2 or negative pi over 2. And so that manipulator's length is 1. So this is 1 here, 2 here, and the total distance here is 2. And then it can also stick out 1 unit this way. Okay, so this is when D2 is equal to 1, it's going to be here or here. And then this D2 can translate, so then this arm can also move and slide that last joint up to here. So it can slide along this line here. Then I know that this arc here, this is going to go from 0 to pi. So it can arc all the way around here, which means that every point on here is also going to follow the same trajectory. But that is hard for me to visualize. So instead of doing that, I'm going to draw the robot at its other farthest extent. So that's coming out this way, 2 units. Again, I've got my prismatic joint. It's pointing downwards, and it can extend either to 1 or to 2. And it can also flip. The only where this end effector is actually going to touch the plane is right here and here. My reachable set is right here. I've got this. Then everything else is going to make an arc around it. So I can just pick things that match. And so these two are going to make an arc here. These two are going to make an arc here. This is my bottom interior. Come around, make an arc like this. And this one will make an arc that comes around like this. So these are my reachable workspaces, and so I can shade those in. I've got two disjoint sets here. And then my last thing I need to do is to label all these radii. So let's label this radii, and we're just going to use Pythagorean theorem. So the distance from here, I'm moving 1 and 1. So this is just going to be square root of 2. Whereas the distance from here to here, I'm moving 1 over and 2. So 1 plus 2 squared, take the root of that. That's just the root of 5. And so here is the root 5. Now a little more interesting is coming out to these outer ones here. So the distance here, I move 2 along my arm and then 1 more over here. So that's going to be 4 squared plus 1 squared. Take the square root of that. No. So that's going to be 1, 2, 3 squared. 3 squared plus 1. Take the square root of that. That's root 10. So a good distance, root 10 for that one. And then over to here, this distance is 2 squared plus this distance here is 3 squared. So that is equal to root 13. So root 13 for that one. And so now I've labeled my radii to each of these, and I've also labeled the endpoints of these straight lines and these curves. And I know it's a little bit messy. I'm not grading on art ability. I just want to make sure that everything is labeled and in there. And you need these in order to visualize where the robot is. Now that we've drawn these out, it is time to solve for the inverse kinematics. And these pictures will help us visualize what those answers are. Inverse kinematics, it's all about building a trig problem that is solvable. So I have this first one, I've got my theta 3 angle in here. And so if I look in my robot, I want to see what sort of things does theta 3 change. So theta 3, its x position, it does modify how far you're extended outwards. But a lot of other things modify your x and your y positions because you're rotating around here and you're extending here. So it's nice to see, is there anything where I can isolate that? And the one thing that stands out here is that I can move theta 1 all the time and I don't change my height of this orange ball at the tip here. I can move this axis here and I don't change the height of this orange ball. In fact, the only thing that changes the height of this orange ball is theta 3. And that's what we're going to work on. So if you look at this ball here, this ball is always 1 unit off the ground, plus 1 unit over here, plus this angle here, it'll be the sine of this angle times the arm length here, which is 1. In fact, I'm going to write out what ZC is first. ZC is equal to 1 plus 1 plus, and I misspoke. So I've got this angle right here. This is theta 3. This arm length here is 1. This length here along here is going to be cosine of theta 3. 1 plus 1 plus the cosine of theta 3. And so now I just need to invert that and I can solve for what is this theta 3. Because I know ZC, inverse kinematics, they give me XC, YC, and ZC. And I'm trying to solve for my parameters. To solve for that, I just say ZC minus 2. And then I can take the inverse of this and I get theta 3. Now there's other ways to solve this as well. In this case, since my range of motion is just between pi over 2 and negative pi over 2, the inverse cosine is always going to be defined on that. But for those of you who really enjoy using the arctangent 2, which is a safer thing to use, we can also write this as the arctangent 2 of this problem. A tan 2, my cosine, my x direction is just going to be ZC minus 2. I can take Pythagorean theorem to solve for my y direction. That's going to be 1 minus ZC minus 2 quantity squared. Put a parenthesis around there. So those are my two answers for that. So the next thing I want to solve for is my D2. What is the extent of this manipulator? And this I'm going to have to draw some triangles. It makes most sense to look straight down on this and then to solve for these triangles. So let's go ahead and do that. Okay, so if I draw my robot, here is my robot looking straight down on it. I've got my first joint coming out here, and I've got my prismatic joint. This is of length 2. And then I've got an extension coming up here and extending out to my revolute joint, which is, this little revolute joint on its side here. And then that can swivel out to either side here, where that length that it's extending here is going to be just the sine of theta 3. This length here, this is d2. If it extends outward, we'll come over here. That makes a right triangle here. And so we want to know, what's this distance here? The position here is xc, yc, zc, but if we're taking the projection down in the plane, that distance here, we'll call that r, is equal to the root of xc squared plus yc squared. This distance over here is still d2. That's the thing that we don't know, but this total distance on here is 2 plus sine 3. That's my little convention here. S underscore 3 is sine theta 3. And so using Pythagorean theorem, we can solve for this unknown. We call this c, and this is a and b, and so c is equal to the square root of a squared plus b squared. And so here, if we square both sides, then we can remove this root expression. And so my c squared on this side is just going to be xc squared plus yc squared. And then my a over here is 2 plus sine theta 3, quantity squared, plus d2 squared. And then I want to know what d2 is, so let's just solve for that. And so d2 is equal to the root of xc squared plus yc squared minus the quantity 2 plus sine of theta 3 quantity squared. And now I've solved for theta 3 and theta 2. The last thing I have to solve for is theta 1. But if theta 3 is negative, then this quantity is negative, and so it's pointing over here. That would still make a right triangle, and this distance along here would still be 2 plus sine of theta 3. So this is correct whether you're out or in. So now let's solve for theta 1. Solving it directly is a little bit harder, but what we can do is we can break that angle into 2 parts. So again, I'm going to draw my robot in here. So here's my robot. First joint is pointing out here, and I have rotated this by theta 1. So the first joint over here, it's extending out here, and I've got my revolute joint extending out here. This distance here is sine theta 3. This angle right here, the x0 to x1 is theta 1. And what I really want to do is solve for that theta 1, but I can't solve that directly. But what I can do is I can solve this angle that goes out to this point here. And then if I could subtract off this interior angle, then I'd have everything that I need. So that's what I'm going to do. I'm going to label this big angle here alpha. I'm going to angle this little angle here beta. Let's solve for alpha first. And then I know that theta 1 is equal to alpha minus beta. And so alpha here, this is the angle all the way to the end. Well, that's just our arctangent 2 of our xc and our yc, the position of the end effector. And then my beta value, well, that's this interior angle over here. So again, I can solve that out by completing my angle. This side over here is d2. This distance here is 2 plus sine 2. So I'm just going to write arc tan. And my x direction, the distance that I'm marching along here, is 2 plus sine theta 3. And then my y direction is d2. And that's what I want. I can write all this in. Just for completeness sake, I'll say that theta 1 is equal to arctan 2 of xc yc minus arctan of 2 plus sine theta 3 d2. But now let's look at the theory behind inverse kinematics. In inverse kinematics, the big idea is that we've got our end effector And we want to figure out what should the rest of the joints of the robot be so the robot connects the end effector in the specified end effector's pose, which is its position, its orientation. So what we're given is this total transformation, where at the end we want the end effector at some rotation R and at some position O. And then we have to figure out how do we set all the rest of the joint variables so that it hands in the right direction. The real robot, how do we solve for that when we're only given this? Yeah, so how do we solve for this when we're only given the end effector? Remember, the total homogeneous transformation H is given by the homogeneous transformations chained together of each joints from Q1 to Qn. We solve this by splitting this up and trying to solve simpler trigonometric problems. And so in our problem, we first wanted to draw and shade the cross-section of the manipulator's workspace. So that answer here was with that robot pointing down, and we get this arc of length 1. And how I grade that, I give 1 point for this radius value, that it's 1, and that I've got a semicircle that goes from negative pi over 2 to pi over 2, and then I give 1 point for being in the correct position. I might have it oriented the wrong way. Now the more complicated problem over here, it's got all of these individual sections. I got these 2 disjoint sets over here with radius from root 2 to root 5. This one is root 10 to root 13. And so I grade it by giving 1 point for each circle. So there's 4 of these little circle segments having the correct radius, and 1 point for shading the outer, 1 point for shading the inner. And then there's also some points for starting at the right position from here to here. Now to solve these inverse trigonometric problems, it's good to just draw this robot. So I've got the interior of the robot. This is D2. This is my prismatic joint 3. And this is the end effector out here. The distance along here is 2 units. The distance that it extends, again, in the same x direction is going to be sine of theta over 3. And then the unknown is D2. I can construct these triangles, and I know the distance of the hypotenuse is going to be, because this point over here is xc, yc, so it's a root of xc squared plus yc squared. And then I can drop that down. That D2 is going to be my xc squared plus yc squared minus the square of this distance 2 plus sine of theta 3. And then if I want to find that angle there is theta 1, and I'm going to solve that by constructing 2 other arcs, which I'll call beta and alpha. So beta is going to be this full angle that's all the way up to where is the end effector. Then alpha will be that interior angle. Now this beta is again given by an arctangent, which is just the x direction and the y direction. Gives me my total angle out there. And my interior angle is also given by an arctangent 2, where my distance along x is 2 plus sine theta 3, and then my y direction is d2. That gives me my answer. Now just to show this works even if the end effector is pointed inwards. So again, I still have 2 units and sine of theta 3, only this quantity is now negative. And then I've got my d2 is my extension along that joint. Again, my end effector is at xc, yc. Again, I drop my perpendicular. D2 is solved previously in step 2. But again, it's the same quantity that we have before, minus sine 3 plus 2 quantity squared. My angles again are still going for, this is theta 1 here, beta minus alpha. So my total angle there, beta minus my interior angle alpha. So beta is the arctangent of xc, yc. Alpha is arctangent of 2 plus sine of theta 3. And we have what was desired. I find it much easier to visualize this robot when I can see it. So here is our robot. We're 1 unit in the air, 2 units over on the radius 1. Then we've got our D2, which is extending in this direction, my rotation over here. This gives me this very interesting workspace here. And remember, the part that was projected onto the plane Z2, Z0 equals 2 is this flat portion here on the bottom. So if we rotate over here, you can sort of see how that's built. And just to show you that it really is the workspace, a top-down view of it. And we can take our theta 1 and is at its 0 position. And so again, it could rotate all the way along this trajectory through here. We'll bring it all the way back to the beginning. If my D2 is pulled all the way back, then we're at the edge of this circular arc here. And so I can revolve around that. Negative pi over 2 all the way over to pi over 2 from this point here, and then I can extend it forward, and that's how we get that straight edge right there. And we can revolve our theta 1 around that angle, and we're revolving right along that circumference. I'm going to flip it to the underbelly. We'll roll it over here, and I'm going to bring this D2 goes backwards. It's retracting along here, so now it's going to follow the interior of that arc as we roll along here. It rolls all the way around here. You can see now it's at theta 1 equals 0, and we can roll our theta 2 around that angle, and we can also get our interior angles here. So I'll roll that over here, and you can see that. So an interesting workspace. Not really sure what this robot would be good for, but now you can see the visualization as well as the solution. So let me end by reminding you that all the answers for these problems are available in the link below, both the problems and the solutions. Now this was an experiment. If you'd like to see more solved out inverse kinematics problems, please subscribe and leave a comment saying that you'd like to see some more problems. If I don't get any requests, then I'll say, well, maybe the world doesn't need more inverse kinematics solutions solved out. But I do have over 4 years of midterms and final exams with worked out problems. So if you're interested, let me know. As always, I hope you're out there making wonderful robots.